intersects, and maybe it goes something like this. We don't care. Okay. But whenever we have a manifold with a boundary, we're kind of particular. Because, it becomes unclear what object are we talking about, and if it contains pieces of the boundary, it might be a pretty boring object. So, whenever we have the existence of such geodesic chords, I mean, it's again a natural question to quantify it and to estimate the length of this geodesic chord in terms of the geometric parameters. Well, in this case, there are two manifolds. There is a manifold M and there is a submanifold M. Now, so one of the examples for manifold with a boundary is a recent result, the existence result of O. But actually, it feels like he proves the older result by Haas and Scott, which said that when we have a Riemannian 2-disk with convex boundary, then there exists at least two simple orthogonal geodesic chords. So, I mean, this is kind of a result, seems like a result in a style of Lyusternik Riemann result. And again, so in this particular case, right, I mean, what should be so simple geodesic chords? They're going to be like distinct, they're going to be covered by anything. So, right, so in this particular case, right, I mean, the most important thing is that we have some flows which don't which allow us not to develop self-intersections as we shorten the curves. And so that's possible, turns out that's possible to do. And now if we want to bound the length, this is a recent result of Isabel Beach. Well, you can do that, except that if you want to bound it in terms of the diameter, you will not necessarily have two distinct geodesic chords, you will bound the length. Not necessarily, they're going to be simple. So that's maybe is a little bit of a not unpleasant situation. However, if you also want the bound in terms of, if you want to allow to use the square of the area, then you have two simple geodesic chords and can bound their lengths. And this, once again, this is reliant on our result with Evgeny and Alex about being able to construct the boundary of the disk over short curves. Okay, so I'm going to go to higher dimension. And so this result, right, I mean, so we know the existence. And now together with this is a long list of authors, so this is about Beach, Heidi Contreras-Pereira, Aaron Griffin, Megan Kerr, and Catherine Serre. We have shown that we can actually estimate the length of this orthogonal geodesic chord whenever we are sure of its existence, which is as long as n is not a deformation retract of M, we have the existence. So in particular, if M is closed and N is closed, there always will be at least one orthogonal geodesic chord. And in this case, we can estimate the length in terms of some parameters of M. Well, I mean, actually, the diameter of M. But the geometry of N will have to come into play. So, in fact, if you want to get a geodesic chord via minimax procedure, in the same paper by Amaral Chava and Hyun Chen, they have demonstrated, well, you cannot do it unless you take the parameters of the submanifold into account. So, so that becomes kind of necessary for the method that we're going to be using. I'm going to discuss just a particular sub-case of this general theorem, just because I don't want it to get too technical. And that's, we're going to discuss a situation where M is a Riemannian 3-sphere. is a Riemannian two-sphere embedded in M. Okay, so in that particular case, I'll give you, so in that particular case, you can estimate the length, so let me just draw a picture. So this is M, and this is M. And there will be a short geodesic chord, and its length will be estimated in terms of the diameter of M. I'll call it little d, diameter of N, which I'll call capital D, and area of N. Okay, so that's all we need to know to estimate the length of this geodesic chord. So one can view those orthogonal geodesic chords, one can, for example, view them as a generalization of geodesic loops. You can imagine if manifold N is a very small geodesic sphere. I mean, if we have this geodesic chord like this, it's just like pick the center of this geodesic sphere, connect it, you obtain a geodesic loop. So it's a generalization. One can kind of view it as a model example of the free boundary problem for minimal surfaces. In terms of estimating the length, I would say this is kind of in the middle between estimating the length of periodic geodesics and estimating the length of geodesic loops or geodesic segments. So it's easier than periodic geodesics, but it is harder than geodesic segments and geodesic loops. So let me just describe the proof. So, so how does the existence, so first, before we try and find the length, right, we should start with the existence theorem. And in order to, so all those theorems are proved to be a Morse serial in an appropriate space. And in this case, what will be the appropriate space? So we want a geodesic loop, we fix a base point and consider all the piecewise differentiable curves based at that particular point, right? So for periodic geodesics, we consider the space of closed curves, right? And in this case, we will have to consider a space of, so if this is N, we will have to consider the curves that begin and end in N, okay? And we'll denote the space like this. So this is piecewise differentiable curves. On M, the endpoints in M. And then let us consider relative homotopic groups. So we consider relative homotopic groups. Relative to N, where N sits naturally in this space, omega and M, because each point on N we can just identify as a constant curve. So now, of course, we hope that, right, so we just need to show that there exists time such that is not trivial. Because if it's not trivial, then we can try and construct it, but we shouldn't be able to do that. And that will give us a minimal object, a critical point of the energy length function on that space. And the critical point, that would be an orthogonal geodesic. Okay. So, well, first of all, we claim that This is the same. Those are isomorphic. And then we get that there exists an I for which this group is non-trivial by studying, let's say, the homological exact sequence of appends and using relative Horowitz theorem. So they exist and we can be assured of their existence. When I'm talking about something specific, I'm talking when M is a Riemannian 3-sphere and N is a Riemannian 2-sphere. And so in this particular case, it's not very difficult to see that I should be 2. So we have a non-trivial. Okay.
May I ask, by logical pair omega nm, you mean you consider them constant loops or loops within n?
I consider constant loops.
Okay.
Yeah, not loops within n, thank you. So, right, so here's, so now what do we do, right? I mean, so what we're going to do is we're going to start with a map. Which is not constructible. Okay. Now, here is a problem, right, that potentially this original map goes through, right? I mean, so we need somehow to gain the control on the length. And potentially this map goes through long curves, okay? So we have something like this, right? This family of curves, right? And maybe some of them are just way too long. But we want, using information about the geometry of M and N, so we want to construct a map a homotopic map of tilde. It is mapped through short curves, homotopic to F. With lengths of curves bounded by some L. L is a function of little d, capital D, and square root of area. Okay, so how are we going to do it, right? I mean, so here is our D. And it is mapped by F. And we're going to subdivide this. This is D2. We're going to subdivide this into tiny squares so that when we look at the image of each of those squares under F, all the curves stay within the epsilon distance from each other. So if I choose a square and I look at how those curves look at the manifold, well, they will resemble something like this. A very thin strip, but potentially consisting of long curves. Does it make sense, everybody? So now I'm going to use this procedure where I'm going to go from skeleton to skeleton and replace my map F, but also show that this map F and F tilde, they are related to each other. Okay, so first I'm going to redraw this. And okay, so I'm going to do nothing to the curves on the boundary. The boundary is mapped to point curves. They have like 0. I'm happy with those. I'm going to start with other vertices, any vertex, okay? And I'm going to, so where does vertex go, right? I mean, vertex goes to a curve, maybe it's a long curve. I want to replace it. What I'm going to replace it is by a minimizing geodesic. So this minimizing geodesic And of course, it's going to have lengths bounded by d, which is a diameter. Okay, so it's unclear what this minimizing geodesic has to do with the original curve. At this stage, nothing. But I'm going to note the following, that I can also construct a family of short curves. So let's say that I'll call this P and this is Q. I can construct a family of short curves that start with P, that connect point P with points on this geodesic, I'm going to call it gamma of T. So P is connected, so there is a one parameter family of curves that connects P and gamma of T, that start with a constant curve and with a geodesic. Now, why this family of curves exists? So it's the first thing that one would want to do is let's try and continuously connect it with geodesics. Well, we cannot do it, right? I mean, there will be a discontinuity. So there will be some points where you have a diagon, and so your geodesics will jump. So there will be this empty space that you want to connect. And unfortunately, you know the following, that if you can connect, if you can contract this curve as a loop, then we can interpolate between those two geodesics that was shown yesterday. But contracting this as a loop in a manifold M has nothing to do with orthogonal chords. So that's not how we want to do. So instead, what we want to do is the following. Okay, so here we have our geodesic diagon. I'm going to draw it separately. And I'm going to say, I'm not going to try to contract it as a loop. I'm going to try and contract, I'm going to just allow those points to push apart. Okay? So I'm going to consider this as just a curve. And the only thing that I want during the homotopy is that the endpoints for this curve, I mean, you'll say this, right? I mean, the fact that the original and final point coincide, this is just a coincidence, I don't care about this. But let me apply the length shortening, and I'm going to insist that the endpoints stay on n. Okay? And so one of the two things will happen, right? I mean, so either this guy will get contracted to a point, or I will get stuck on a orthogonal geodesic chord. Okay, so if I get stuck on the orthogonal geodesic chord, that's a good thing. No, stuck, sorry, George. Of length at most 2d, okay? And case 2, it will contract to a point. So now let me just follow what happens with the endpoints of those curves, right? So as I try to shorten legs, the endpoints will describe the trajectory that will look like this. Now, if I can now, so now I'm in N, okay? And N is a Riemannian two-sphere. So if I can now continuously connect this point by short curves in N, if I can do that, that will allow for me to contract the original loop the original loop, the original diagonal as a loop. Because I can do something like this, for example. And just connect those. Just connect them like this, okay? So now the problem becomes, I mean, if I want to build this family of curves that I want, the problem becomes, I have a loop in N. Can I come up with a short family of curves that connect this to this point P? And the answer is, well, I'm going to try doing something similar, right? And what I'm going to try is, well, okay, so I have this in N, I have this loop in N. So let me just try to connect this with geodesics, no, geodesics in N now, that's where the diameter of N going to play a role. Well, that's not the only thing in particular. I will not be able to do it because there will be a discontinuity. There will be those geodesic diagonals coming to points of N. So this is a length bounded by D, and this is a length bounded by D. And I have to fill in between. But I can fill in between because I can use the theorem with Evgeny and Alex to construct this as a loop. And the length of curves in this loop will be bounded in terms of diameter and square root of area of N. So in this particular case, and what do I obtain? I obtain something like this. So let me return to the original problem. Just looking for the bound. So the bound is something like, I don't know. So the bound, so let me return to the original problem. So remember, I started off with a potentially long curve, and I wanted short red curves to connect. And the length of those curves will be bounded by something like 2D, maybe plus, I don't remember, 203D. Something like this, if I remember correctly. Okay, so, but in any case, right, I mean, you can see that we can bound the length of those curves as promised in terms of the diameter of M and diameter and area of M. So what do I do next, right? I mean, so now, right, I mean, so remember at this stage, I only have extended, right? I mean, I started with this guy. And thus far, I have only extended this to zero skeleton. Not extended, changed my map on zero skeleton, I should say. I would like now to change it on one skeleton. So for each of those edges, I would like to come up with a map F tilde. Okay. So what would I do, right? I mean, so right now, under F, what I see in my manifold is a long thin strip of curves. Those curves are very close to each other within distance epsilon, but potentially very long. What I also have is I have this guy. I mean, I have a short family of curves connecting like this. I have a short family of curves here, right? I mean, so for each vertex, I can do that. So I would like now to have, and what do I notice, right? I mean, that by this simple lemma that I like to cite, if I look at this as a loop, I can contract it to a point over short loops, because I can simply use those auxiliary curves to connect points here, cut across, that will only add the distance of epsilon, and then follow another red curve back to this point right here. So I can contract that as a loop. So what is then my map of tilde will look like? Well, I'm going to start with those geodesics that I have constructed. I'm going to add little short segments to those geodesics. That's not going to be a problem. until I get to the middle of this curve right here, and to the middle of this curve right here, well, we'll have a discontinuity. By the prior lemma, it can be filled. Okay? So remember, if we can construct a loop over short loops, there is a path homotopy. So there is a path homotopy between this guy. I'm going to use a different color maybe. There is a path homotopy between this guy and this guy. Okay? Over short curves. And so my F tilde is going to be exactly that. Okay? And you can say, well, that it doesn't appear that this F tilde has anything to do with F, but you see I can change F to F tilde in a continuous way. Because you see this whole procedure that I've done, I don't have to perform it right away to this whole strip, but I can do it in stages in the following way. So, okay, so this is my original strip. I can say, well, let me cut it right here. I'm going to keep the original curves. I'm going to keep the original curves, and I'm only going to replace those curves right here. And then I'm just going to glue them together, glue the families that I obtained right here, and glue them to these long curves right there. And when I glue them together, that gives me a homotopy. So now this is, I've changed my map on the two skeleton. Okay. And so what do I do? Sorry, I changed my map on one skeleton. So what do I do when I go to two skeleton? So when I go to the two skeleton, I do the following. Right. So I look at each little square. And this little square, again, corresponds to the following strip on a manifold. It's a two-dimensional, it's a two-parameter family of potentially long strips. But all those long strips are very close to each other. Now, from the last step, from the actually first step, from the zero step, I have this auxiliary family of curves connecting this guy to each of the, corresponding to each of the vertex, all those red curves. Now I can do the following. I can repeat the whole procedure. So, I will now draw all the strips. But I'll take a point here. I continuously will connect it by short curves. Now, I will do the same here. I will look at all those thin strips which are now of dimension 2, and I will repeat the procedure from the previous step. I will rotate this frame, and repeat the same procedure, which will allow me to define things on the two skeleton. And once again, I don't have to do it all at once. I can actually do it in stages, just cut and repeat this, cut and repeat, and so those long curves get replaced, continuously replaced by shorter curves, so those maps are going to be homotopic. So that's kind of a summary of the proof. So now let me just briefly, as much as I have time, talk about curvature. As you have noticed that it seems that at least using the methods that we know, speaking about stationary one-dimensional objects, not all, things are a little bit different with nets, but I don't have time to talk about those. It's important to know how to construct a loop in an efficient way so that we can estimate the length of curves, or the length of curve of those loops, right? I mean, so we start off with a loop on a manifold, and we would like to construct it so that it goes through short loops. Now, actually, we don't have to necessarily construct it. I mean, I don't know if I'll have enough time to mention it. I mean, it's actually enough not to contract it, but to significantly shorten its length. But we still want to shorten the length of the loop in an effective way so that we can control the length as we shorten it. And so, in general, we don't know how to do it, okay? And it seems like an obstacle to doing that is a geodesic loop. But if you want something other than geodesic loops, then it's not particularly, or if you want many geodesic loops, then picking is not that helpful. So, then curvature becomes helpful. And we have a bunch of results. So there are, which use some older and some new. So one is like starting from the volume estimate on convex hypersurfaces by Tribergs. I mean, Kroc might have also had such estimate, I don't remember. There is 1/4 pinched metric of positive sectional curvature of Baumann, Torbergson, and Ziller. There are estimates on manifolds with section curvature bounded by also the space KVD space. The space where curvature is bounded below by K, volume is bounded below by V, and diameter is bounded above by D. There is a result of Nanwu and Zhou for bounded richer curvature, but only in dimension 4. Now, here's a recent result that I've mentioned in passing, that if you have a convex Riemannian 2 sphere, then the length of a shortest periodic geodesic is bounded by 3 times the diameter. So this is kind of interesting because, well, we don't know what the sharp bound on a 2 sphere should be. So it's interesting, at least, with positive curvature, we can do better than 4D. Now, so let me just discuss briefly why those things work. So those things work for the following reason. Now, so when we have the manifold, the KVD space, right? There is a paper by Grovey and Peterson, which tells us about so let me just maybe state it. And this is for any that the collection MDKV contains only finitely many homotopy types. Okay, so and the paper is based on the following. I mean, so first of all, right, so why do we want, what technique do we want to use when we have a sectional curvature bounded below? So this comes in terms of using Toponogov's theorem, Toponogov's comparison theorem. In particular, it allows one to estimate distance between critical point of distance function. So one thing that we use is Toponogov's theorem. And Another thing that we use here is volume comparison. So section curvature is bounded below, ridge is bounded below. So we can use volume comparison theorem. And when we combine those, it allows us to somehow control local geometry of a manifold. And this comes in terms of the estimate for the contractibility radius. So, I mean, it would be nice if we could cover our manifold by small number of balls with bounded injectivity radius, but we cannot. And the second best thing is something like this, that we can cover it by finitely many, and the number of those balls can be estimated, of balls, of metric balls that maybe look like this. They don't have to be even simply connected, but they are contractible in a slightly larger ball. Now, if we can do that, in some cases, and so all of those things can be estimated, we can do that. And in some cases, we can effectively construct loops. Now, I mean, I will not have time to describe it in detail, but right. So now here's another result. This is, let's say we have a manifold. Here is a problem. I don't know if you have nothing else to do during discussion session. You can try that. So this is how does curvature possibly help to contract things? Okay, so now here's
that was too fast.
It went too fast. Okay, I'm going to just. Okay. So, right, so there is a classical theorem to Panokov that states that simple closed geodesic Riemannian two-sphere scalar curvature greater than or equal to 2 have length at most 2 pi. Now, there is also the theorem of Rademacher that if you have positive Ricci curvature, then the length of a shortest periodic geodesic is bounded by pi times n. Okay? So, in particular, if we rescale, right, I mean, if Ricci is bounded by n minus 1 over r squared, then the length of a shortest periodic geodesic can be bounded in terms of the lower bound of the Ricci curvature. This is actually an improvement both in bound and in the proof itself of my prior estimate for the length of a shortest periodic geodesic on a positive Ricci curvature. And so what's important, right? I mean, so what is important, what's behind this proof, right? I mean, this proof here relies on Banner-Meyer's theorem. So in particular, the important part is that if we have a sufficiently long loop of length bounded by pi, we can always shorten it. So if the loop is long, we can shorten it, right? I mean, this comes out of the proof of Banner-Meyer's theorem. So now having those results, this is kind of a natural question, except it comes before the Ricci curvature result. But I guess, it makes it more natural. So let's say we have a manifold with a positive scalar curvature. Can we bound the length of a shortest periodic geodesic in terms of this lower bound for the scalar curvature? And, okay, sorry. So together with the Evgeny and Maximo, we have proved this result in dimensions 3. So we prove this hypothesis in dimensions 3. So let me just talk just a little bit about how to prove it. Well, we still want to be able to construct loops. We will not be able to, so in, this is, so first of all, right, I mean, so let me say this, right, I mean, so in, so most difficult case, as always, is a simply connected case. In particular, well, three-dimensional manifolds are classified, and the closed three-dimensional manifolds are classified. So as soon as we have this result for a three-dimensional sphere, it will be done. It will just follow for the rest of the manifolds. So the first step is the result of Lyusternik maximum. I am missing an arrow here. Which said this, right? I mean that let me focus on a Riemannian three-sphere.
May I ask,
Yes.
is there something mysterious behind the number 13 in point C?
I don't think this is very significant. I think this is just a number that they got. So, I mean, in order to sort of say where it comes comes from, right? I mean, it comes from estimates for the area and diameter of the minimal surfaces of index 0 and 1. And then, you know, you do something to them and it becomes what it becomes. So, right. So, so what they have here, right, I mean, is that in dimension 3 in particular, right, I mean, you start off with a three-dimensional manifold. They map it to a tree. And when they look at the inverse image, right, I mean, they get spheres, okay? And sometimes they will bifurcate like this. Or they get something like this. And what's nice about those spheres, is that those spheres will have a small area and they will have the small diameter. What's bad about this is that the diameter is only going to be small in the ambient space. And we do not necessarily know how to control the diameter or the intrinsic diameter of each of those spheres. Now, so why is it significant for us? I mean, if we so in fact, right? I mean, this brings us to Orison width. I mean, so this Orison width is small in this case. But it's better than that because we can also control the area of those spheres. So why is it interesting to us, right? I mean, so if you go back to the proof of Crookes' theorem. In Crookes' theorem, what did we do, right? We started off with Riemannian two-sphere, and we used short curves to subdivide the sphere into domains, and then we swept out those domains. And here we're doing something like that. We would like to use small spheres to break this into domains, and then sweep out those domains. Except we are sweeping out by spheres, not by curves. So this is a little bit unpleasant that we need to sweep out by curves, not by spheres. Now, it is, I think, is important to understand where the scalar curvature comes in, right? I mean, so the scalar curvature comes in terms of the following, right? With the following inequalities. So first of all, right, I mean, we have that if we have a stable minimal surface, it's closed. Then diameter is less than or equal to 2 pi divided by square root of a. Now, so this is a result of Schoening and Gromov-Wilson.
What is K here? What is K?
Oh, this is a lower bound on this scalar curvature.
Ah.
So now also in the same case, the area is bounded by sorry. I think I'm getting confused about the so the area is bounded by pi. Okay, Shane, yeah. I might be wrong about diameter. Okay, I don't know what this constant is. Okay, I'm confused at the moment. Now, similarly, if we have a minimal surface of index 1, we get similar bounds. And those similar bounds, they are, well, the diameter bound is an observation. Is an observation by Lyusternik and Zhou. And the area bound, this is Marcus and Nevish. Okay, so let's keep those things in mind. And what do we do, right? I mean, so okay, so here is step 1. So step 1 is that we are going to take our M, and in this M, we are going to find a maximal collection of disjoint, strictly stable, minimal two spheres. So we are going to obtain subdomains that look something like this. So index 0 for all those spheres, and we remember that we know well, we can bound the diameter and area. So now we started over with this sphere, and it's partitioned into those Swiss cheese domains. So after we're done with this, we're going to take one of those domains. We're going to take each of those domains. And by the work of Daniel Ketor, Liakumovich, and Antoine Son, we can find inside a minimal surface. And the index of this minimal surface is going to be bounded, so the index is bounded by 1. But our original collection of the disjoint minimal spheres was maximal, so that means the index of this guy is 1. So then we're going to, so we further partitioned it into Swiss cheese domains, and those Swiss cheese domains look kind of like this. Where one of the boundary components is large in terms of the index. And what we're going to do next is we are going to just wiggle this a little bit so that its area decreases. Then we apply, well, I mean, in the paper with of the curvature and Maximo, they applied the mean curvature flow and showed that it converges to those guys. So you sweep out those guys by spheres. But we are a little bit unhappy about this because here is a problem. While the area decreases, when we do this, the diameter, actually just in one step, it might increase. So, so there was a little bit of modification done that this is a discrete curvature flow where we don't have full control over the diameter, but we have a better control. We're going to have a better control over the diameter of those spheres. So I'm not going to go into technical details. I'm just going to say that this is the case. So now, let's say we have done this. This is now swept out by spheres. Well, we want to partition this into short curves. So, and again, keep in mind that we don't necessarily know how to effectively construct loops in M. However, let's pretend that each of the sigma, each of the surface sigma has both bounded area and bounded diameter. Who has both bounded area and bounded diameter? You can recall our theorem of Lyusternik and Nabudovsky that any loop here can be constructed over short loop. So we cannot construct loops in general in a manifold, but we can construct them when they lie on each of those two spheres. So now, yes.
So this diameter is extrinsic diameter, right?
It's something in between. I don't want to get into this. So the diameter of these guys might be quite large. They can increase. You shorten the area and all of a sudden the diameter goes up. But they're going to lie, so the good thing is that they're going to lie very close to a sphere with short diameter.
Okay.
And because they lie very close to a sphere with short diameter, you can actually push it to the sphere and contract it there. So, right. So now what do we do, right? So yes, we know that we can now construct loops on spheres, and we hope that this is helpful. So this is what we're going to do. Now we can actually, right? Let's start. So we know that our M is the Riemannian three-sphere. So I know that M is a Riemannian three-sphere. So there is a diffeomorphism, 3 to M. We know that M has a sort of structure, right? A structure that it has, that it's kind of decomposed into spheres, two-dimensional spheres like this, right? So we have a sphere, then it bifurcates, etc., right? We have those bunch of spheres. So there is a tree-like structure of spheres in this M. Can do exactly the same in S3. In the standard round sphere, we can just pull this structure to S3. Kind of decompose it into two-dimensional spheres, where it looks like this. Now we can consider a sweep out by curves of those guys, right? So in fact, what we're considering is a map D2 to the space of closed curves. Well, on S3, okay? And then we can, it will induce a map of D2 to the space of closed curves on M, okay? But those closed curves might potentially be very long. So, let me just describe how we construct this. So we have S3. let's just take a neighborhood of this tree. This will be our disk. The boundary will be mapped to constant curves. The boundary of this disk will be mapped to constant curves. So this is a sweepout. This is a not contractible, non-contractible map. But you know the curves. If you look where those points go, right? I mean, so let me just look at the slides. Where does it go? I mean, it goes to a sphere that is partitioned into curves. But some of the curves might be quite long. We don't know that they're short. And so now the thing to do is, well, I mean, so if you recall the proof of this short orthogonal segments theorem, we just started off with a map and we replaced it by a homotopic map that goes through short curves, and we're going to do exactly the same thing. We're going to partition it into little squares, and we're going to replace the map in an analogous manner. So I think I'm out of time. I'm going to stop here.